Okay, I guess we're recording. That's good. So we covered a bunch of force problems. We didn't do all the force problems that we could have possibly done. There are more in these things here. But we're going to move on to friction. Really need to get that assignment fixed here. So anyway, so there are two types of friction in the world, and friction is always caused by surfaces rubbing together. If you zoom in on any two surfaces that are rubbing together, you'll see that there is some structure to that surface. Even if it's smooth, it'll have some kind of structure to it. It looks almost like mountains up close. And as those mountains kind of try to roll past each other, they resist the motion, and that's why we call it resistance. The two types of friction are static friction and kinetic friction. Static friction is the friction that two things have if they're not moving against each other. As soon as they start to move, it becomes what we call kinetic friction. Why do we call them something different? Well, if you've ever pushed a box along the floor, you know that when you first start pushing, it's really hard to push it. And then once you get it going, it's easier to push it. And the reason for that is because once you've got these kind of mountains rolling past each other and breaking through each other, it's easier to keep it going. It has its own kind of impetus, you know, the inertia of it, and also the momentum of it just kind of help it to keep going, so that the friction actually resists less, right? So that's why we treat them differently, because they are quite different. The static friction can react to the pushing up to a certain point. So if I have my little tape thing here on my tape dispenser on my table here, and if I push on it with just a little bit of force, it will push back with that same amount of force, and the tape thing won't go anywhere. So it's just sitting there, right? If I push a little bit harder, it still pushes back with enough force to stop it from moving. But eventually I will push it hard enough that it will start moving, and it'll actually be easier to push it a little bit. Not much, but a little bit. And so this thing can provide up to a certain amount of frictional force to keep itself from moving. But once I get above that amount of frictional force, then it starts to move. That's why we have a less than or equal to symbol here in this formula. The static frictional force is going to be less than or equal to the normal force on the object. Remember, the normal force is the counteractive force to the weight. So you have the weight of the tape dispenser and the normal force from the table back up, right? So that normal force, if we take the magnitude of that, which on a flat countertop is just the weight of this. If it's on an incline, it's less than the weight, but if it's on a flat thing, then it's a weight, the weight of the tape. So you take that normal force magnitude and you multiply it by what we call the coefficient of static friction, and that will give you the magnitude of the frictional force. Now, what direction is the frictional force? The frictional force always opposes movement or impending movement. So if I'm pushing this way, then the impending movement is in the same direction of my push, even if it's not moving. If it did move, it would move this way. So that's why we call it impending movement. So the friction is acting this way because my push is this way. If it's actually sliding, then the friction acts in the opposite direction of the movement every time. So the maximum static coefficient friction, the maximum static friction that you can have on an object is equal to mu s times normal force, and it can provide anything less than that as well. It just depends on how hard you push on it. If the maximum amount of static friction is 10 newtons, and you push with 7 newtons, the object is only going to have 7 newtons of friction to oppose it. And then if you push with 8 newtons, it will have 8 newtons. If you push with 3 newtons, it will have 3 newtons. It can do anything under its maximum for any given situation. Well, what is this mu sub s? It is actually just a measured thing. People go out there and they take this tape guy and they put it on a table and they actually measure the forces of pushing and then they calculate the forces of friction from it. And then they calculate this static coefficient of friction for every single set of surfaces they can find, in every condition they can find. And there are literally just millions of these things online. You can go and look up the static coefficient of friction between concrete and jello if you wanted to. And I'm sure somebody has measured it or something like that. And you can see here that we have rubber on dry concrete has a static coefficient of friction of 1, which is really quite high. And that's good because tires, you don't want them to slip on concrete. You want them to stick and not move, right? So it has a high coefficient of friction. On wet concrete, it's lower. So wet tires will slide on wet concrete much more easily than they will slide on dry concrete. Wood against wood is also about as low as tires on concrete, on wet concrete. Waxed wood on wet snow is much lower, 0.14. Here you go all the way down to this one, bone lubricated by synovial fluid. Right, that's the lowest one we have here. Bones lubricated by synovial fluid, that's your normal bones with the normal stuff in between them. And you get 0.016, very, very slippery, very, very non-friction. When they replace this, they replace it with Teflon on steel. Not as good, right? 0.04 static coefficient of friction means that it's more friction. So bigger number, more friction, smaller numbers, less friction. This one being the smallest one we have on this, in this particular table. So what is kinetic friction? Well, kinetic friction is what happens when the thing actually moves. If the thing is actually moving, there will be friction against it. And it's actually the same formula. It just has an equal sign and a mu sub k instead of a mu sub s. Where mu sub k is a different number in this table for moving things. So while the object's not moving and you apply a force to it, if you start pushing with this force here, the frictional force, the static frictional force increases and increases and increases until it gets to its maximum. And then after that, when it starts moving, it drops down to a slightly lower level and has this kind of steady friction depending on the materials that are rubbing against each other. Here they actually show the artificial knee replacement right there. Here's the real knee, here's the fake knee. So here is the classic example, a person pushing on the box, right? It's a 20 kilogram crate. The coefficient of static friction between the crate and the floor is 0.7. The coefficient of kinetic friction is 0.6. So they've told us mu sub s and mu sub k here. And they're going to push with this horizontal force, P, and P is going to be 20 newtons in part A, 30 newtons in part B, 120 newtons in part C, and 180 newtons in part D. And we're supposed to find the force of friction for each one of those. The first thing to do when they're asking you to find the force of friction is to determine whether the thing is moving or not. Sometimes they'll just tell you it's moving. In this one, it's at rest on the floor. So this one's not moving when we start the problem. So we have to, if it's not moving when you start the problem, you have to figure out what is the maximum coefficient or what is the maximum friction for static friction of this object. That's the first thing you'll have to do if the box is not moving. If the box is already moving, then you don't have to worry about the static coefficient of friction. You can just worry about kinetic friction and calculate it and be done. But this one, we have to worry about static friction. So you can go ahead and make your diagram with your forces on it and everything else, and that's great. But what we want to do now is to calculate that friction. The first thing we're going to calculate is the weight, because we need the weight. 20 kilograms times 9.8, 196 newtons of weight. And the weight and the normal force are going to add together to be 0 because the box is not moving in the vertical direction. So the normal force is going to be equal to the weight, since those are the only two forces in that direction. So the weight and the normal force are equal to 196 newtons in magnitude from this equation here. Now the other equation says that the two forces, the other direction, has the two forces, the pushing force and the frictional force. Well, we'll get to that in a second. So, first thing we have to do then is we have to say, what is the maximum force of static friction? And they calculate that right here. This is the normal force, 196 newtons. This is the coefficient of static friction. So this is mu sub s times n for static friction force. 137 newtons. And what that means is that this box, no matter how hard you push, as long as you push with less than 137 newtons, this box will not go anywhere. This box will not move until you push harder than 137 newtons, because that's how much friction it can supply backwards. Okay? So he pushes, he starts off pushing with a 20 newtons in part A, right? 20 newtons. So there's a 20 newton push right here, and the box pushes back with 20 newtons because it can supply 20 newtons of friction. So the friction in part A is the same as the pushing force, 20 newtons. In part B, pushes with 30 newtons. That's still not more than 137 newtons. So in part B, the box pushes back with 30 newtons of frictional force. So the frictional force from part B is 30 newtons. And of course, if we're talking about directions and 20 newtons is the positive direction, then it would be friction would be negative 20 newtons, right? Because it's going to push backwards. In part C, he pushes with 120 newtons. Now he's getting close to moving the box, because the box will move as soon as he pushes with something more than 137 newtons. But it's still not quite enough. It's getting close, but the box will still push back, and it will push back with 120 newtons of friction, and the box will still not move anywhere. However, in part D, the person pushes with 180 newtons. So the box is going to start sliding. And when it does, it's going to switch to kinetic friction. So we switch to kinetic friction and calculate the kinetic friction, which is mu sub k times n. And we already know the normal force is 196 newtons, and we use the kinetic coefficient of friction 0.6. And it turns out there's 118 newtons of kinetic friction once the box starts moving. So in part D, he makes the box move. He pushes with 180 newtons, and the box pushes back with 118 newtons. That means we have to take the pushing force minus the frictional force to get the total force. And that ends up equaling 62 newtons. And you take that 62 newtons and divide it by the mass to get the acceleration of the box at 3.1 meters per second squared. So that's one of two tricky types of friction questions. The one where the object is not moving to begin with, and then it starts to move. Because then you have to calculate the static friction maximum, and any force that is lower than that maximum will not move the box, and the friction will push back with the same amount of force. But once you get to that maximum force or beyond, then the box will start moving, and you can get you can calculate, then you get kinetic friction. You calculate the kinetic friction and subtract it from the pushing force to get the total force. Now the other type of tricky question when it comes to friction is the inclined plane. When things are sitting on a surface that is not horizontal to the ground, then the weight of them, of course, is the same, but the amount of their weight that pushes them against that surface is different. Because only part of their weight is pushing them against the surface, the other part of the weight is actually trying to make them slide down the surface. And you always see this happen. If you have an object on a surface that is inclined, and you sit it and you put it on the surface, it might slide, it might not, depending on how much friction there is. But if you lift the surface, eventually the thing will slide down, because less and less of its weight is actually holding the object onto the surface. So this part of the weight that is perpendicular to the surface is actually equal to the normal force at this point, which is less than their actual weight. This is just one component of the weight. So you use a rotation of axes, put x in the horizontal direction, horizontal to, or rather perpendicular, no, sorry. X is parallel to the surface here, and y is perpendicular to the surface here. And then you redo your problem here, so you resolve this weight component into a y component and an x component. And then you have a new free body diagram where you're using the y component of the weight and the normal force being equal. So that's the sum of the forces in that direction. And then the x component of the weight and the friction adding together to equal mass times acceleration, because the skier can accelerate in that direction. Once you've got that done, you still have to decide whether or not the object is sliding already or moving already. If the object is moving already, then you just have to calculate kinetic friction. If the object starts out at a standstill, then you have to calculate the maximum amount of static friction again, and then figure out if the push, or if the overall force here is actually going to overcome that. In this case, they tell us a skier is sliding down a snowy slope at a constant acceleration. So we already know that the skier is moving, and we know that they're accelerating, right? So we know that there's a total force in that direction. So we can just go right to the kinetic version of friction, and we calculate the normal force as equal to the y component of the weight force, mg cosine 25 there. Cosine 25 because it's this one, which is next to the angle. And then we use that normal force, mg cosine 25, and multiply it by the kinetic coefficient of friction to get the friction in this particular problem, the kinetic friction in this particular problem. So once we've done that, then we're good to go. However, in this problem, they don't give us the kinetic coefficient of friction. Here they actually want us to calculate that kinetic coefficient of friction. They tell us the friction is 45, and they want us to find mu. So we go ahead and solve for mu and plug in 45 newtons, and we get 0.082, which is pretty normal for a skier. Probably needs to put a little wax on his skis. Really interesting. There's really interesting science being done with this lately. There is a microscope called an atomic force microscope. And the way an atomic force microscope works is they have a surface that they're trying to understand the roughness of a surface, or they want to map out what a surface looks like. And this would be the surface down here that's got this roughness to it. But this rough surface, I'm saying, is like smoother than the smoothest glass you've ever seen. Okay, so it's super smooth. But it still has roughness to it. It's just very difficult to see. So what they do is they have this arm that comes out that is kind of like the arm on a record player. The arm on a record player kind of balances out there with that spring. That's what it's like. It's very well balanced, so that it can just barely. It doesn't really actually even touch the surface that it's scanning. It just kind of scans past it. But instead of just a regular old needle down here on the end, it has something really impressive. Let's see if we can find an image of it. This needle is usually very, very tiny. So this is what it would look like if it was put under a normal microscope like this. That's what you would see. If you put it under a very high-powered but fairly normal microscope, it would look like just kind of a sharp tip like this. However, if you put it under what we call a scanning electron microscope or a tunneling electron microscope or something like this, you would see that at the very end there's even a sharper bit of it down here. And this sharper bit here can be very, very tiny. We're talking just a few atoms across. Here they're showing this area, this line right here is 5 microns, and you can see that this is much smaller than that. This line is 5 microns long. This is much, much tinier than that by far. And same here, you have 10, 1, 5. But everything is much, 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 each one of these little needles is much tinier than that. A micron is 10 to the minus 6, and an atom is 10 to the minus 10, right? So essentially, if we've got 5 microns here, and this needle looks like it's about 1/10 of that, so it's maybe 0.5 microns across. So that would be 500 nanometers, which 500 nanometers would be that's probably even smaller than that at the tip. It's probably I would say it's probably more like 10 nanometers at the tip, so super tiny at the tip. And they actually don't even show one. At any smaller scale. They can do the smaller scale. But I would say it's more like about 10 nanometers. 10 nanometers is about 100 atoms, which is just phenomenally small, super tiny. So why? Why do they do this? Well, because at that very tiny scale, it's like you have these atoms here that are rubbing against other atoms and experience a kind of friction. All atoms have electrons around them, right? And as these electrons encounter each other, they push against each other like friction. They actually repel each other like friction, which is actually what real friction is all about, is these rubbing electrons. So as they run into an atom, that needle will actually bump a little bit. It will actually rise up a little bit. And when it rises up, there's a laser hitting it on the back of the needle, and there's a little mirror. And then it goes a fairly long distance over to a detector. And as that arm bounces, that laser jumps a little bit, and the detector can detect that jump. And then they can make a map of different things that they're looking at. They're not really looking at it, they're just scanning it and detecting small things in it. So this is the kind. Then once they've detected the surface, they will actually make an image out of that detection. So in this particular case, they're making an image of I don't know what this is actually, but it looks like 2, 3, 4. It looks like some hexanes. So hexane is a group of 6 carbon molecules with hydrogens around it. So this looks like some hexane molecules. Let's see what else they've got. They've got streptavidin. I don't know what that is either. Probably some kind of drug. But they're molecules. They can look at the structure of molecules. The smallest thing they've ever done is they've actually mapped out gold. I think just plain old gold that's been hammered out, like this one here. So in this case, this is gold-plated graphene, it looks like. So this is a lattice of graphite. Kind of like pencil lead, essentially. They've done other ones that are kind of interesting too. Anyway, they're always doing some kind of mapping of these molecules in the atom. And what they're trying to do is they're trying to see if the atoms are really kind of put together the way we thought they were put together. Because we've never seen most molecules and atoms before. Like, it was the first molecule that we actually ever saw was a DNA molecule, and it was back in 1950s, the 1950s. That woman at the top of that poster actually was the woman who did that the first time. And then it was 2 other scientists got the credit, got the Nobel Prize for it, because she died before the Nobel Prize was awarded. You can't get the Nobel Prize after you die. But they discovered the DNA molecule, and the reason they could see the DNA molecule was they used X-rays, which is a very small wavelength of light, so they could see this very, very small thing, which is the DNA molecule. And the DNA molecule was so big compared to other molecules. Like, if most molecules are like little cars and houses, DNA molecules are like skyscrapers in the molecule order. They're humongous compared to most molecules. So they're quite large and quite easy to see. But besides that, we've not seen very many molecules at all, or had any idea of what they could look, what they really do look like, or how they're formed. We're still not really looking at them with this force microscope, but we are getting an idea of their structure to see how they're kind of put together. So that's quite interesting science. That's only been around for a few decades now. It's not very old. So the atomic force microscope. This one's a fun problem. On this one, you have two blocks sitting on top of each other, sitting on the ground. So you have friction between the floor and the first block, friction between these two blocks, right? And then you have a tension between the two. That's a fun one. Here you have a truck that's moving forward, and of course it's the friction between the tires and the road that allow the truck to move forward. But then you have the box that's sitting on the back of the truck, and the thing that's keeping the box on the truck is friction once again. So friction everywhere. And of course, sliding down the ski slopes is friction as well. Since we started a little bit late today, we're going to just stop with friction, and I'm going to let you work on some homework. I can't remember what's in the homework. Let's take a look at that really quick. No, I haven't added any, but I kind of wanted to wait to see how far we got before I started adding questions. So let's, what is my password again? I remember what it was. Here it is. So, we have 3 questions in here. One of them is rotation. That's the first one. Next one is pendulum. And the last one is helicopter. Okay, we're going to add in some basic problems, mostly friction, I think, to get us started here. I think I like that one. We'll add the superhero problem. Let's do some friction. Okay, this one I'm going to give to you, but I want to explain it a little bit. In this problem, you have 3 different situations. One where you're pushing sideways. This one we've done before. This is one of the examples we just did. However, this one we're pushing sideways and down a little bit. And when you push something sideways and down a little bit, you actually push it into the floor a little harder, which means the floor is going to push up on it a little bit harder. In other words, the vertical component of this force actually increases the normal force. So the normal force in this problem is the weight plus the y component of this force. And in the third one, you're pulling on it and pulling upward and to the right a little bit instead of pushing. That means you're lifting the block off the ground a little bit. So in this third one, the normal force is a little bit less. Okay? In this one, the normal force is a little bit more, so the friction is going to be a little bit more. In this one, the normal force is a little bit less, so the friction is going to be a little bit less. Keep that in mind, and this problem won't be too difficult. Okay, let's see here. That one's already in there. Okay, I think that's probably good for the moment. I will add more as we learn more. So The stuff that's at the beginning where we do the circular motion, you don't necessarily have to do that stuff right away. We can wait until I get back or until I post another video. Now, we've got 11 questions.
These are all the questions that are
Yeah, for now. We probably will add some more later once we've looked at some more. But some more of some more of the chapter, but we've not seen the last couple sections of the chapter, so we'll decide on those later. All right. Any questions before we break? Okay. You too. All right. After turning in and out. There's some soup and bread in there too, if you're interested. Homemade.
So, I took this picture, and I knew it was going around in a circle, but I don't know how to find the angle in the first place, so I was like, well, I don't know how to figure out where it starts.
Okay, so we go, your first point is that your acceleration is,
Yeah, I don't think it's acceleration.
oh, well, the acceleration tells you where it is because it's going in a circle, right? The acceleration always points towards the center of the motion, right?
Right, but it's just
So, your acceleration, your first acceleration is here's your axis, right? Your first acceleration is -7 I half.
wait, so this is actually where we're system is equal and this thing's over here.
X,
X
X
is
equals, so this is now Z. So your negative X, and it's moving as much like an I J, so it's an I Z. Okay, so it's going negative X, so that's negative 7, 1, 2, 3, 4, 5, 6, 7, and positive negative.
I knew it was over here.
So it's pointing up this way right now. That means, that's the acceleration. That means if your object would have to be out here somewhere for the acceleration to be met. Okay? The acceleration is this way. It's moving in a circle. When things move in a circle, the acceleration is always toward the center.
Oh,
So it
right.
must be
So it
this
would
way.
have to be over there.
Now, the next time it is at 7, negative 7. Right? So 7I is right here. 7 and negative 7. First one is negative 7, negative 7. So the first one is actually here. So then the second one is 7I. So it's when you go back to 7 out this way.
And negative, which means
Negative 7 which is this way. So the next one is over here. Right? That's the next acceleration. Which means it has to be down here. That's what it is. Right? And because they both have 7s, we know the angle here is 90 degrees.
that's imaginary where the travel. But the figure.
So if it goes through a 90-degree angle in 5 seconds, which would say, T equals 5.4 seconds, right? Then a quarter of its motion in 4 seconds, how far does it go in a full motion? 4 times that.
Well, what are you pulling that from?
It goes 90 degrees. It goes 90 degrees in 4 seconds. How much is one cycle? All the way around the circle.
Oh, I see what you're
360. So it's 4 seconds times 4.
Thanks.
Yep. Alright, I'll see you later. I'll be back in a week.
Alright, I'll try to get some of my cat work organized and started like,
Will do. Students will be in and out. Of course, Thursday they're here for that. The students will be in and out taking grain samples.
I'll keep the doors open. They get here till, they usually go with 2, 3.
Most of them are cards will work too. I think I got them all in. Micah's I didn't do because Micah's just going to do 2 days for this week and I'll do the rest of it. But Micah will need to come in a couple of times. But yeah, if you just kind of keep an eye out, and I'll see you later. Got to stop.